All right, let's do this. Getting down to it. I think we're down to about maybe two more lectures. Uh, I'm starting to think this is okay. I've been doing this like after dinner. Right now, I'm drinking a beer. I don't even like beer, but I'm drinking a beer while I'm giving a lecture. It's just think you could do. Just something you just can't do in the past. So it's grown on me a little bit. So I definitely miss lecturing with you and actually interacting with you. But drinking a beer sitting in my bedroom, not so bad. Okay. Like I said, I think we're gonna make this work. I think we're gonna make it through here. I've updated. Oh, I guess I told you this before last time. Is I've updated the breakdown of how we're gonna grade this class. So, well, let's dive in. Let's do an example. That's on our agenda today. Is to do a laterally unsupported or a beam that has intermittent lateral supports as opposed to having supports along the entire length. Okay. And so when you have, just a quick review, when you have these braces that are spread out instead of supporting the entire top flange, you get this thing called lateral torsional buckling. You get lateral torsional buckling in between these braces is what you would get, okay, in between these cross braces or these lateral braces here. But it's just like before, like all of our other I guess things that we've been designing. There's these capacity curves that are floating around rather. When our supported length, there's some slenderness ratio for like flange local buckling. It was H over, what was it? It was BF over 2TF was the slenderness ratio. For web buckling, it was H over TW. And in here, the instability is going to be based off of our unsupported length, how big this LB gets. If LB gets really big, then lateral torsional buckling is going to be more of an issue and our capacity is going to go down. So we get this capacity curve that goes like this. Okay. And then, at the end here, if the LB is small enough, plastic moment's going to control. If LB is greater than LP and less than LR, then inelastic lateral torsional buckling, and then elastic lateral torsional buckling will happen if our LB is bigger than LR, right? And so it won't form a plastic hinge. Now, how you go about designing these things, it gets pretty complicated because there's a lot of stuff going on here, right? And so, what's in control of this? We looked at the equations, okay? They're functions of A, E, I, J, C, W, and F, Y, right? It's going to be properties of the material itself and the shape, right? And so those things are going to kind of control if lateral torsional buckling is going to be an issue, but then also this unsupported length is going to be an issue. But then also the support conditions. How much of the compression flange is in compression, right? Or how severe is the compression flange or the compression on the compression flange, right? And under normal bending conditions, it would be the top flange. This would be a case where this is more severe than this. Okay, so the one on the left is more severe than the one on the right because in this case, the whole top flange is in compression, whereas here, only this middle part is in compression. And so we need some factor to float that accounts for that. And that's what the CB value is in there for. The CB accounts for that. Worst case scenario is a constant moment on either end. You have the worst case compression on the top flange across the entire length. It's the most severe over the entire length. Whereas this case, right, it's actually zero at the end, zero compression, and then it goes up to the maximum and then down. Here would be the maximum across the whole length. The worst case scenario, CB is equal to 1.0. Right? Other than that, CB gets bigger than 1 because it increases our capacity. Worst case scenario is this. You get rewarded if you don't have this, is one way to think about it. And so you increase your capacity, right? And we talked about how do you calculate CB. You use this equation right here. And here are some of the values. We're going to do that in the example today. We're going to calculate what CB is for the different spans. They have some pre-calculated values here that you can use as well, right? And so CB, we just talked about calculated CB, that's important. But then how do you design for this? Because we looked at the equations. These equations right here that have these values in there, very long, very big pain in the ass. You would not want to try to design based off of those equations, right? It just wouldn't work. You could solve for like the required I or the required J or something. It just makes it too difficult to do it that way. So AISC is no dummy, okay? And they've come up with this way of doing it. And what they have is they've gone through for every wide flange section, okay? Because usually these bending is going to be based off of wide flange. For every wide flange section that they have plotted these moment capacity curves. They have VMN on one axis and LB on the other axis. And they've gone through and plotted all sorts of them, right? And this table 3-10 takes up many, many pages. They look at a little snippet here, and then they look at a little snippet here, and they look at another snippet here, and another snippet here. So that's actually that's exactly what they're doing. Each page is doing this, right? And you can imagine these things go on for pages, because there's all sorts of curves. There's another curve over here, there's another one over here, there's another one over here. And so each page is splitting that thing up into different things. Okay. And so, but then it gets a little complexity, because this guy right here is set up for CB equal to 1, the worst case scenario. These are only made for CB equal to 1. Well, can we still use them if CB isn't equal to 1? And the answer is yes. What we do is we take our moment demand and we divide by CB. So the CB is on the capacity side, but you take the CB and you put it on the demand side. And when you do that, it kind of think of it as adjusting these curves. But you gotta be careful, because these things, right, it would be equivalent to coming up with shifting these things to the right is what it would be. It would be by dividing the demand by CB. But you got to be careful, because that CB value does not affect the plastic moment capacities. Okay, it affects this part of the curve down here, but it doesn't affect these flat parts. And so you just have to do a check afterwards to make sure it's okay. And we'll illustrate that in the example. Okay, and so how you work these things, you come in, you plot your MU and LB on your curve, right? And then you read up and to the right, and the first solid line is going to be your most economical. Okay, so let's do it. So here's our example. We have a simply supported beam that has a distributed load on it, right? A uniformly distributed load, and it has 0.18 kips per foot is what that load is. The U on there denotes or implies that this has already been factored, whereas the PL, so and same thing with this, this 128 kips, we have a live load 128 kips in here. So we don't have to factor these two loads. Okay, they've already been factored based off of that little U out the front. So we just kind of skipped that step. But with this particular beam, the top flange of this beam is supported at 18 feet from the left here. So that's 18 feet. So it's supported there, and then it's supported 12 feet over again, or you can think about it 18 feet from the right. And so it has some lateral supports there. Now those are lateral supports. So those supports are going into and out of the board. They are not doing this. They're not supporting it like that. So they're not going to affect your deflections. They're not going to affect your moment and stuff like that. They are just there. They matter when it comes to looking at lateral torsional buckling. Okay. I think your homework problem has you calculate deflections. Well, the deflections will not be a factor of these lateral supports, right? These things are acting into and out of the page here, and so they're not going to affect what's happening in the vertical direction. Okay, so here we go. 128 kips is right. The other thing is, right, when you have multiple loads like this with a distributed load and a point load, you could use superposition. Hopefully you saw that when you did your last homework, that you're not going to find a case in the back of the book that has a distributed load and a point load. They'll have the distributed load as being a case and a point load as being a case, and then you just have to you take both, use the law or the law of superposition, but you take advantage of superposition, and when it's elastic, you can look at just the point load, just the distributed load, and then look at their responses and then add them together. That stands for calculating the moments, that stands for calculating the shears, and for calculating deflections. You can do that. Okay, so there's the case. What we need though, we're going to calculate what CB is, okay, and we're going to do it two methods. Let's actually add that to the thing. Let's say design this beam. So this is going to be part of the problem statement. I never really actually put a problem statement on here. Design beam for loading conditions indicated. First, assume CB is equal to 1.0, which is going to be conservative, or maybe conservative. Then calc CB and design with values. Okay, and so that's an important thing to say. You don't have to, and this is I got to be clear here. You do not have to do both of these things. Well, I mean, obviously right now when we do this example, you do need to do that, okay? But when you're doing a design, you don't have to do CB equal to 1 and then design it, and then come back and change your CB value. You don't have to do both of those things. We're just doing it here as an illustration of just calculating CB or not, and looking at the benefit of doing so. Okay. So then there's that. So to calculate CB a little bit later, we need to know, obviously we need to know what the demands on this. We need to know what MU and VU are for this thing, right? We need MU and VU for this because we obviously that's going to play into the design. But we also need to come up with an equation for the moment as a function of x. The reason I need to do that is because I'm going to calculate CB. CB is going to be a function of what your moments are along the length of this thing. So I need to know how my moments are changing, or what my moments are going to be at different locations along the span. So I need a moment as a function of x. So there's a little bit further step than we've done before in this class, at least. Usually you just draw the shear and moment diagrams. So now we need to draw the shear and moment diagrams and come up with an equation for the moment and the shear. Okay, but this is a pretty simple case. We could do that pretty easily. Okay, so let's get started here. So let me take a sip out of my beer here. You guys will respect me more if I drink beer, right? White Claws. I've been trying some White Claws lately. Maybe that's more hip these days, is to have White Claws, not beer. But I've tried both. I really like White Claws. Okay. Okay. So let's draw these shear moment diagrams. So the usually what you do, you come up with what the reactions are going to be, right? The reactions on either end for the shear diagram. I'm going to break this thing up, and I'm going to do the dead load first. So we're going to do VU dead load. What's it called? V dead load. We'll know that these are already factored. V dead load, moment dead load. And then we'll do shear live load and moment live load. Okay, and so we'll break it. We're just going to look at superposition and take advantage of that. Okay, and so to get this reaction, you always start out with reactions. The reaction is going to be WU times the length, which is going to be 48 feet, divided by 2, right? And then what you get is 4.32 kips, right? When you carry that out. And again, this is just the distributed load is what you get. So this thing's going to start out at 4.32 kips, right? And then 3 above on the side. Right here. And then it's just going to have a decreasing, right? The slope of this line is just going to be the negative of the distributed load right here. And so it's just going to be constant across the whole thing. And this thing will close. Let's see if I can nail it with my... No. I think that I'd be able to draw a straight line with the help of a... Yep, there we go. So that's what our shear diagram is going to look like. Right? That's what it's going to look like. But then like I said before, we need to know what the equation is for this. And so VU as a function of x will be, it's going to start out at 4.32 kips. And then its slope is going to be the negative of the load that's applied. So it's going to be negative 0.18 times x. Right? And you look back at your mechanics and materials to see where that came from, but that is how it's defined. Okay. Right. It's yep. Okay. There's a couple of different ways to come up with that, but that's usually, I start out, it needs to be 4.32 at the end. We know that the slope is going down negative, that it's going to be the negative of what this load is right here, and then that gets multiplied by x. Right? And so that's what our shear is across the length. The moment, mu of x, is going to be the integral of that. Integral of v dx, which is going to be 4.32x minus 0.18x squared over 2. Okay. Plus a constant, right? You pick up a constant. In this case, though, we want our moment to be 0 at the end, right? We know that the moment's going to be 0 at the end. It's going to be 0 at the simple support. And by imposing that, it tells us that this constant right there is going to be equal to 0. Would you look at that? Okay, that constant is going to be equal to 0 because we know the otherwise you would have a moment at the end, when x is equal to 0, and we don't want it, so that constant goes to 0. So there's our moment equation for the distributed load. So we're going to need that. Let me mark that as something we need a little bit later. Okay, and so what that will look like, again, is going to be, the moment's going to go pretty good. Pretty good. Okay, and so that moment, right, it starts at zeros at the ends. Right, and so this, so I guess that's what our moment equation is. So we know what that is. Okay. Okay, so now let's look at what the shear is from the point load, right? The shear from the point load. So that shear from the point load, it's going to have a reaction of PL over 2. Reaction is going to be equal to P live load divided by 2. Right? There's just one point load coming down. Right, and then that just gets distributed into the two reactions on the side. So that's just going to be PLL over 2, which is, didn't even write that down, 128 over 2. 68. Okay, and then the slope of your shear diagram is going to be the negative of what W is. And W is 0, right? The distributed load is going to be 0, so it's going to have no slope. And so this guy is going to come across where the point load is applied. And it's going to jump down to there, and it's going to go across to the end. Right? And so there's what our shear diagram is going to be. There's a lot of stuff that's floating around there, but right, the point load in the middle, there's going to be a jump, so it's going to go P over 2, and then since there is no distributed load, it's going to be constant across here. The point load is going to jump it down, P, the live load, the 128, is going to go across at 68, and then it's going to get bumped back up. 68 the right? No, it's not. 128, 64. You let me finish. 64. Okay, that's what the reaction is. So this is 64. 64 kips, right? But I need the moment, okay? The moment equation is just going to be, I guess let's write what shear is. Shear, the live load, as a function of x, is going to be PL over 2. It's going to be 64 kips. This is for x less than L over 2. Right? 6 is less than L over 2. That's only when this is only valid for that. When x is greater than L over 2, it becomes negative 64. Okay, but we just need to know what's happening on before L over 2. So at this point, you could take the moment. My live load is a function of x, and that's just going to be it's going to be the integral of the shear again. It's just going to be 64 x that's it, 64x. But again, plus a constant. That constant's going to go to 0. Oh, why does it draw a brick? Okay, this is going to be 64x, right? And so that's only to L over 2, so it's going to look like this. I'm going to do that in a moment with green. Okay, that's what our moment diagram is going to look like. Right? Once it goes to L over 2, it's going to do something different there, but you can see that it has the slope of 64 going up and then a negative slope of 64 going down. So there's our moment equation for the live load, 64x. And so the total equation, mu is a function x. This is what we need for calculating CB. This is going to be, right, you just take them together. You just add m dead load plus m live load, and what you get is 68.32 x minus 0.18 x squared all over 2. So that is our moment equation. And again, where that plays in is when we go to calculate CB. Okay? There's that. So I guess we need it for CB and we need it for the design of this thing too. Right? And I'll show you in a second here. It isn't just for calculating CB because we're designing this for each interval, and each interval that we have to design this for is this interval, and then this interval, right? So I need to know what the worst case moment is across this interval. So I need to know what the moment is right here, which is not up at the top yet, right? And I guess I always start down this path of like, how do I explain this stuff? Oh, if I just follow my notes, I explain it in my notes. That's exactly why I designed my notes in the way that I did. Okay, so here we are. Right, so there's kind of the moment diagrams that we need for solving this thing. So the next thing is the first thing we're going to do is solution, capital M, 1. Okay, and this is going to be CB equal to 1.0. Okay, let's do that one first. Remember, you don't have to do both of these. We're going to do both here just as an illustration. So we're going to look at interval number 1 first. Okay, so interval 1 is going to be this interval right here. From here to here, we'll call that interval 1, right? Because you have to do one of these designs for every one of these spans. Now, you might be asking yourself, well, right, because here, the moment is going to be less, right? The moment's going to be less, but the unsupported length is going to be 18 feet. Here, for this span right here, this is going to be interval 2. Call that interval 2. Right? Interval 2, this guy is going to have a bigger moment because it's in the middle, right? But its unsupported length is 12 feet, okay? This one has a lesser moment, but a bigger unsupported length. This one has a bigger moment, but a smaller unsupported length. So right off the bat, you don't know which one controls, right? You don't know, is it the one with the bigger moment and the smaller moment and the bigger unsupported length, or the one with the bigger moment and the smaller unsupported length. You don't know. So what you do is you design for each one of those, okay? So interval 1, we're going to do that one first. So interval 1, it has a moment, it has an LB. Right off the bat, you can see that. LB for interval 1 is going to be equal to 18 feet, right? Because that's how big the span is between supports. You have a support here, and you have a support here. And so there's 18 feet in between them. So that unsupported length is LB. And then MU, the worst case moment is going to be at 18 feet. Okay. MU of 18 feet is going to be 1201 kips. Right? Where did that kip feet? Where did that come from? That came from, I just plugged in 18 feet into this equation right here. Plugged 18 there and 18 there. And what you get is 1,201 kip feet. Okay, so 1,201 kip feet with 18 feet of unsupported length. So at this point, we have everything we need, especially since CB is equal to 1. We have everything we need to look into those tables, right? Because what you do is you plot these two values on that table, and you read up and to the right, and it gives you the beam that you want to use. Okay, so right here, table 3-10, what we're looking for is something over here that says 1201, right? 1305. Let's make sure a phi end is on this axis. This is the ASD. This side is ASD. This is green in your book, right? We want to use this is for allowable stress design. This is LRFD. We want to use LRFD. So what we're looking for down here is 1200, 1201 in fact, right? And so 1200, yeah, there's 1200, right? So 1201 is going to be, just slightly above this line that's going across right here, okay? And then we have to find 18 feet. Look like I've already marked it here from last time I taught this class. So we go 1200, 18 feet, 1200 across, 18 feet. And so we're right at this point right here. right? And then anything up and to the right will work. So technically, a W24 by 131 will work. Oh, it looks like a W33 by 118 would work. A W30 by 132 works. A W21 by 147 works. And a W33 by 130 is the first solid line we come to, right? And you can see that is the lightest weight beam that would work, right? W33 by 130. So 130 versus 147 versus 132 versus 131. And so this would be, if you were aiming for the lightest weight section, a W33 by 130 is the one that you would use for the design there. Okay, so we jump back up and you say, right, let's just write that down. So you say, yep, this would tell us that a W33 by 130 would work. Okay, and we don't have to check that versus PMP, the plastic moment capacity, because we did not do any adjustments for CB because we said CB was equal to 1. So according to this design, interval 1 would need a W33 by 130. So then we go over to interval 2. Right, we're done with that one. So we come over and do interval 2. Okay, interval 2. That would be, like we labeled up here, between here and here. So now I need the worst case moment in the middle. So that'd be at L over 2. At L over 2. And so my moment demand would be MU of 24 feet. Right? If I plug in 24 into that equation up there, we get 1588 kip feet. And then LB for this beam is 12 feet in between 12 feet in between those supports. So this is what our demand is that you have to design for in this case, for this span. A 1588 kip feet and an unsupported length of 12 feet, right? And so again, you're comparing, look, this has a bigger moment versus 1201, but this has a bigger unsupported length, 18 feet versus 12 feet. So it's not clear which one controls, okay? So at this point, we go to that same table down below, and now we're looking for 1588. Right, 1588 is not on here. We need to look at the page that would be right above this. Right, it would be the page that would be right above this, or I don't know if it's in that order or not. 3108. It's not in that order, but it's not the page right above it. But like if this was to keep going up, what that table is. Right, so here is the one that has 1500 on it. We're looking for 1588, 1560, 1599, close enough. And then it has an unsupported length of 12 feet. So you go 1590 over to 12 feet, 10, 11, 12. And so it puts us right there. Okay. And at this point, you read up and to the right. It looks like the first thing we hit's that solid. That solid is a W33 by 130. Okay. And I think you can see it. Yeah, you can see it up there too. W33 by 130. So according to that interval there, it would be the same size beam. It just happened to be that way. It isn't always that way. Right? It's not always that way. It just so happens to be in the example that we're doing here. That you get a W33 by 130. Okay? And that's that, right? So there's their design, right? Right? At this point, you would have to compare which one is bigger. So, sometimes they're not the same, and you would look for the one that's bigger. Sometimes it's going to be really obvious. If it's deeper and heavier, it's probably going to be the one that's deeper and heavier. Sometimes there might be a little bit of clouded stuff, and in that case, what you would have to do is go look in those tables and see if you could find the different beams and where your demands fit on there for those different beams. So it might be a little more complicated. Usually, one stands out as being the beefier, bigger beam. Okay. At this point, you're not completely done. At this point, you would have to design for, all right, you just say check and deflections. Okay, this would be same as before. Laterally supported beams. Okay. So there's nothing new there, right? Literally, you look this sucker up. You'd look this sucker up in your Z tables. It would tell you what phi VN is. It would tell you what your I was. You would look up to see what the deflections of a distributed load and the point load phi WL to the fourth over 384, PL cubed over 40 ADI, right? You'd have those deflections and you compare those to the limit. So we're not going to cover that as part of this example. I just want to demonstrate to you this whole how you go about using these tables and when you have CB values and stuff like that. So according to this, W33 by 130 would work. You'd have to go check the deflections and the shear as well, which is probably, it's really easy to do that. It's the same as you did in your last homework. It's not too bad. Okay, so let's go on to the next step. Okay, so this would be the more complicated way of checking your capacities here. This is by calculating CB. Okay, so this would be division 2, right? Or just, I made the problem statement part A and part B. So solution 2, calculate CB. Okay. And so you do the same thing. You come down and you look at interval 1 and interval 2. Okay, so interval 1, let's do that one first. Okay, interval 1 first. Right, the moment diagram for interval 1 looks like this. Right, we haven't drawn this before, but just to kind of give you an idea of where we're looking. Right, it's going to go something like that. Right? It's going to have a little bit of straight line, a little bit of parabolic, and it doesn't actually it kind of doesn't flatten out, okay, because it's only the first 18 feet of it. It's probably something like that. A little bit of curve, a little bit of straight to it. This distance here, let me take that color, right, is only the first 18 feet, right? There's the 12 feet right next to it. Okay, there's 12 feet right next to it. The next unsupported length is 12 feet. So this is just the first. This is just the first span there. Okay, and so we calculated what this was already, but this is be 1201. Right, this is what we got from the last one. This would be 1201 kip feet. Right, that's MU of 18 feet is that. Okay, but what we need is we need MA. MA, and that's going to be MU of 18 feet divided by 4, right? Because that's this distance, that's this guy right here, right? Remember MA, this is the quarter point. One quarter L, 1/2 L, and then 3/4 L. Right, it's where this would be MA, MB, MC. Right, and then this is M max. Okay, the one on the far right here is M max. Okay, and the L in this equation right here, this L, right, it's not the overall span, it's just the span of that interval right there. So in this case, it's 18 feet. So it's 1/4 of 18 feet, 1/2 of 18 feet, and 3/4 of 18 feet. Right. So this MU of 18 over 4 is what MA is. This ends up being equal to 306 kip feet. Then we come down, we calculate MB is, that'd be MU of 9 feet. Did that in my head. 18 over 2. 608 kip feet. MC would be equal to MU of 318 over 4. It shows that the 3/4 of that 18 feet, this ends up being 906. Okay, and then M max is 1201. Okay, so those are all the values that you would need for going into that equation for CB. I'm going to cheat. It's pure laziness. Drink a beer, hanging out at my house. Be lazy here. That's how I calculate CB. In this particular case, has probably more work to just write the damn equation, but at least you know it's right this way, and you can read my writing. Right? If you plug in all the values above into this equation, you get CB is equal to 1.67. Okay. So this case right here, this case is not right that severe, right? The compression in that flange, right? It starts out near zero, or it is zero. Sorry, compression is zero at the very end, and then it works its way up to the worst case on the right, right? But then the rest of it really isn't in. I mean, we don't care about what's happening in the rest of the spans because we're just looking at the first 18 feet, and in the first 18 feet, it's not that severe. So your capacity is 67% higher than what you would calculate in those equations, or it's the capacity is 67% higher than what you would see in those capacity curves. Okay, and so that's a pretty big deal, right? And so it is worth calculating CB typically, right? We're going to see in this particular case the middle is a little bit different. The middle span's a little bit different. I'm going to bump that to the right. Okay, so there's how you calculate it. If you go to interval 2, we haven't designed for this yet, but I'm just going to calculate what the I values are first. Interval 2. Okay, interval 2 is the middle component. Right. It's the middle part of it, and it's going to look like this. Okay. As again, that's just this. That is just right, this part right here, right? So this is interval 1 goes, from here to here. Sorry, here to here. So the moment's going to go like this. And then the middle one's pretty close to being flat, and then it goes down, right? It's kind of this middle component added with this middle component right here. So it's pretty close to being flat across the middle, okay? And we're going to see the results of that. So that's what that middle one is going to be. And this distance right here is 12 feet. Right. And so I'm going to leave that to you to calculate what that CB is. But what I got was CB equal to 1.02. Right. I think you guys, hopefully you get the point from doing this one up here, how it works. This case, it would be going from, this would be MA, this would be MB, this would be MC, and this would be M max. It would be the one up at the top right here. And when you plug those values into here, you get CB is equal to 1.02. Okay, the other thing to note about this is just be careful when you enter it into these equations right here. This one, it starts out at zero, and then it goes out to 18 feet. When you do these calculations, you do have to take into consideration right, that moment diagram. The equation starts way over here, right? So your x starts 18 feet over, right? And so when you're using that moment equation, this isn't just, this value right here isn't 1/4, well, sorry, swore a little bit. All right, it's one of those things where it's like, I wish I could show them how to do it. Well, if I quit being so lazy, I could show you. MA would be 18 feet. MA would be equal to MU of 18 feet plus 12 over 4, right? And then MB would be equal to MU of 18 feet plus 6. Right, and so on. And MC, same deal. You just have to make sure you have that 18 feet out front, because that equation that we developed, right? That equation that we developed was for starting at the far left, okay? Might as well write this, I guess. So MC is equal to MU, 18 feet, plus 3 times 12 over 4. Right? And those are equal to something. It's equal to something. It's equal to something. M max. M max is 1508, I think, right? We calculated that before. 1588, rather. You might double check that you can get that number. Also, I did that. This is me in my head. I think that this is all right. Okay, but you get CB equal to 1.02. And thing to note there, look at that. CB is almost equal to 1, right? Is that okay? Is that right? Is that what you're supposed to be at? The answer is yes, it is supposed to be at that. Because look, the shape of this is pretty dang close to the worst case you can have. It's the worst case moment over almost the entire length of this thing, right? It starts out at a high moment and it ends at a high moment. It's not quite a constant moment. Remember, CB equal to 1 is a constant moment across the whole thing. It's not quite that, but it's pretty close to that. And so the CB is equal to 1.02. So you can see that calculating the CB for this middle span isn't going to affect our answer too much from before, because before we assumed CB is equal to 1. Now we just calculated CB is dang close to being equal to 1 in this particular case. And so our beam that we should get should be about the same size as the previous one. It just so happens, and the reason we get that is because this middle span is pretty dang close to the worst case scenario you can have, okay? But regardless, let's just keep going with it. That is kind of what we need for our demand, right? We got CB is 1.67 and CB is equal to 1.02. But at this point, we just do what we did last time when we look at the design. We go interval 1 first. Let's look at that. Interval 1. Now our demands, we still have an unsupported length. We say MU. Now let's do LB first. LB again is 18 feet. It's the same. And then MU is equal to 1201 kip feet, right? But then that's not how we enter the table. Since we're going to take advantage of CB equal to 1.02, we go in there with an MU adjusted, right? MU adjusted, and that's going to be 1201 divided by 1.67, right? And this ends up being equal to 719 kip feet. Right? And so we enter those tables with, instead of entering those tables with 1,201 kip feet, we enter the tables with 719. And so you can see this could be way beneficial, right? Right? It could be way beneficial. You could take advantage of having a CB not equal to 1 and a CB equal to 1.67. And so we get to design for 719 instead of 1,201. Okay? So if we enter those tables, what do we say? 719. So 719, right? There's 720. Unsupported length of 18 feet. 18 feet's over here. And look at that. I've marked it. 720, 18 feet. Puts us right there. Reading up into the right. Almost a W30 by 90 works. It might work out there, but I'd read it up into the right, and that would give me. Trace that sucker down. Trace it to be 27 by 94. No, you know what I'd picked before was a W30 by 90. I think I said that we were okay right there. But also, if you read up into the right from there, you could also get, trace this guy down. 27 by 94. I'll pick this guy just because it's lighter, and that's what I've done before. You're pretty dang close right there. So W30 by 90, right? Just because I have the other tables in the figure below so we can look at it. So this would tell me that we would pick a W30 by 90. Right? But since we adjusted for CB, we have to compare. This is this is the rule you just have to remember to do, right? Since we adjusted by CB, we have to make sure that the unadjusted moment demand is less than PMP. And this has to do with the CB affects lateral torsional buckling limit states. It does not affect the plastic moment capacity. So right now, that's what you would do, is you'd say, okay, is MU, this is just the rule to check, is MU less than or equal to PMP? Okay, question mark. Okay, and so this is the unadjusted MU that you check. So this would be 1201 kip feet, right? And you check to see, is it less than PMP? Well, what's PMP? Well, you have to look up what PMP is for W30 by 90. So you go to the Z table. So you go to the Z tables. Look at that. I just happen to have them right here. So W30 by 116, 30 by 99. So this is W30 by 90. Okay, so that's the one we said we were going to use. W30 by 90. PMP is this column right here. And so that's 1060. So the plastic moment capacity of a 30 by 90 is 1060. And so we have a problem. Right? And so this would say that is greater than 1060 kip feet. Okay? What this tells us is the plastic, so this is no good. Okay? What this tells us is the plastic moment controls. Okay? And at that point, let's go to the Z tables. Okay? You would go to the Z tables for this guy. Okay? And so we jump over to the Z tables. Okay, at least that's how I would do it. It doesn't say that exactly that. I'm not sure if it's super clear that it's always going to be the plastic moment that controls, but it controls the design for this particular beam of that size. And so you go to the Z tables. You're looking for 1201. When I see a 1201 in here, I got a 1200, so 14 by 176. But you wouldn't design for 14 by 176, right? Because it's heavier. And so you read up until the first bold, and what you get is a W30 by 108. Okay, so W30 by 108 is what I would say you would come up with the size of this thing. And so this would say, design this thing as a W30 by 108. Right? And you'd have to make sure that it works for shear and stuff like that as well. And this is where this is just that little check, right? We would have ran into trouble. We would have ran into some trouble if we would just designed by 1.67 and said, yep, this is a W30 by 90 would work. It doesn't work, right? It does not work. It would mean that a W30 by 90, you would form a plastic hinge before you reach this thing right here. Before you hit the actual 1201. You'd have a plastic hinge before, and the thing would fail prematurely. And so you have to check to make sure that this happens. In this case, it didn't happen, and so now we know if we design it as a W30 by 108, that works, right? And if you wanted to make sure absolutely that a 30 by 108 would work, you could come back and you could compare the 719 and 18 feet again. You should be able to see that. See if you can on this table. So what do you say? 719 and 18 feet. I don't know if we're going to be able to see it on here. What did I say? What did we say that thing was going to be? W30 by 108. Yeah, well, you could see that it would work. There's a 30 by 99 right there. So if a W30 by 99 would work, you could see that a W30 by 108 would be someplace over to the right here. And so it would definitely work. Okay, and so this one would say, yep, W30 by 108. And then you'd have to go check. You got to check deflections and stuff like that. Okay, but that's only interval 1. So let's look at interval 2. Right, interval 2. Right, that one we've kind of already done, right? Interval 2, CB was equal to 1.02. Right, we already did this for CB equal to 1. LB, I guess LB was 12 feet, and then MU adjusted, right, would be equal to 1588. Or no, sorry, MU is 1588, but MU adjusted is 1588 divided by 1.02. And then obviously this is pretty dang close, 1556 kip feet. Right? And if you look this thing up at the table, it'll give you the same size beam as we had when we assumed CB was equal to 1, because it's pretty dang close for CB equal to 1. So from the tables, it would tell you that you'd need a 33 by 130 is what it would say you would need. Okay, and then you would check. I mean, in this case, again, probably don't need to check it, because if CB equal to 1, you don't have to do this check, but you'd have to make sure, just to stick with the rules, that MU is greater than that. So this is, you could be comparing 1588 and make sure that it's less than VMP for W33 by 130, which is 1750. Right, and so it's okay. Right, and so the beam design that you would use is this guy right here, right? So you'd be comparing, right? You're not going to change the beam size halfway across the span, and so you'd be comparing a W33 by 130 to a W30 by 108, right? Which one's going to control? Well, this one is deeper and heavier, and this one is shallower and lighter, and so it's going to be this one controls. Okay, that one controls, and then at this point you would have to go, check shear and check deflections and shear. Okay. Boom. Okay. So there is beam design. Okay. For steel. Right? Things get a little bit more complicated. If you go on to get a master's and stuff like that, you dive into all sorts of different things associated with. Our next topic is going to be columns, okay? But we're only going to look at columns with similar to the other one, with just concentrically loaded, with no moment on them as well, right? So you can think about grad school and taking, advanced steel classes and stuff like that. You would take into consideration, bending and axial load at the same time, right? You'd look at built up sections. So instead of just using a wide, all these design aids and stuff like that are straight up for wide flanges that are made in a factory and they have all standard sizes. What if you have a built up section where you took a couple plates and welded them to each other and made them work, which you're allowed to do, right? And in some cases, like in big beam design or big bridge designs, that's what you do. You make these big plate girders, like big plates, and you weld them together. Well, how do you check the capacity of something like that? You have to dive into using some of those other equations, right? But for this class, right, this kind of ends our beam design aspect of this. And also keep in mind, these tables assume standard properties. If you change the yield stress of your material, right, these tables are no longer valid anymore. You have to make the assumption that it's made out of the standard material, okay? So steel design classes would cover that. Connection design, like how do you connect these members to each other? How do you get a moment resistant connection versus a simple connection, right? You dive deep into how do you attach steel to concrete, right? Because most foundations are made out of concrete, right? And so anyways, just to give you some topics there. The last topic that we have to cover is going to be axial loaded members. In those cases, in axial loaded members, we got to worry about buckling. Okay, buckling is going to be an issue. Local buckling, global buckling, stuff like that. Okay, and so again, we're going to see some more capacity curves. That's what I had. So now you should have enough to go through the rest of your homework. Okay, that is due, I believe it's due on Friday. So hope everybody's doing well. Take it easy.